Okay, hi everybody. So I thought I'd go ahead and do another video on going forward on some material that's going to be on the third exam in the finals. So I'm going to start chapter 18. I am still going to go back and do another video on the exam format and kind of how you can expect how that's going to go next week. And so that will be coming up in another couple of days. And I know that's on everybody's mind, but for right now, I just thought I would go ahead and kind of go into the next chapter, just as I have a little bit of time and it's quiet in the house at the moment. So this chapter deals specifically about talking about reactions that occur at the alpha carbon position. And this is something that we have mentioned before in class about alpha carbons and the kind of the nature of the hydrogen atoms that are on those alpha carbons. And so I'm going to start by kind of reviewing a couple of those concepts. So if we were to take a carbonyl compound and we were to go over, let's say, to a couple of carbons out here and here, and I were to color in those hydrogens, so the hydrogen atoms here at this position, this is the alpha carbon, so these are referred to as the alpha hydrogens, and then these hydrogens here on the end, okay, these are your beta hydrogens. And I apologize if this is a little bit washed out. I've tried to play around with this just to kind of make the color stand out a little bit better, a little bit more brightly. So it may affect the focus. My hands are not normally this red, but let's just see how this goes. So this set of alpha hydrogens right here, these are alpha hydrogens. Those alpha hydrogens have a pKa of roughly about 19 to 20, and they are much more acidic. They are much more acidic than a typical carbon-hydrogen bond. A typical carbon-hydrogen bond on a carbon that's sp3 hybridized, its pKa value is generally in the range of about 45 to 50. Okay, so we're talking 10 to the 25th, 10 to the 30th more acidic for these hydrogens right here. Now, that is to put this in line with these hydrogens, okay, right here on this beta carbon. They fall into this category and are much, much less acidic. And so the reason for this acidity has to do with obviously the carbonyl. Now you can think of the carbonyl as inductively removing electron density, but I think one of the things you should recognize here is something about the nature of the conjugate base. So if I were to, let's say, redraw that compound showing these alpha hydrogens, and if I were to treat this with, let's say, base B, okay, that could deprotonate that hydrogen, all right, I'm going to draw this so that the electrons go onto that carbon atom right there at that position. So this is going to be the conjugate base of that acid, where I have a lone pair here and a negative charge. All right, and there's our hydrogen, and then what's remaining, and then the CH3. And what you want to recognize here is that that lone pair is in fact in resonance with the carbonyl. So you have a resonance stabilization. Okay. And this species is collectively known as an enolate, okay? An enolate. Resonance stabilization of the conjugate base equals stronger acid. Resonance stabilization of the conjugate base equals stronger acid. Okay. Now, this is one type of species that we're going to see present here. But there's another one that you should be aware of too, which is, well, what if we were to put, let's say, that compound with alpha hydrogens in acid? What would happen? Okay, so you guys tell me as I'm drawing this out, what is the first step of the mechanism? Okay, and if you said protonation of the oxygen, you are on the right track. That is the first step, protonation of the carbonyl oxygen. Now, as soon as you do that, that is now making these alpha hydrogens right here at this position. These are now very acidic, okay, because now the oxygen is positively charged, and that is pulling electron density out of here like crazy. So that means that even weak bases like water could potentially deprotonate these systems. And so that gives you a compound that looks like this. And this should look familiar. This is something we saw at the end of chapter 17. It is where we have an alkene, and an alcohol. And so we refer to this as an enol. Okay, and you should see that there is a resonance structure here that I could draw so that there is negative charge buildup again at that alpha carbon position. So what's important to know here is that when you put compounds with alpha hydrogens in acids, you end up forming enols. And when you put them in the presence of a base, they end up forming enolates. Okay, so that'll be important when we start talking about their individual chemistries. Now, this process where you have a compound that is essentially going from its what we call its keto form to its enol form, this can even happen where the molecule can effectively react with itself and do this on its own. That process is what is known as tautomerization, which was something that we mentioned in the last chapter. So tautomerization is where compounds with alpha hydrogens can exist in an equilibrium in an appropriate solvent with their enol forms. So generally the solvent will facilitate that process, but it's identical to what we were talking about a moment ago. Now, if you looked at acetone, acetone clearly has alpha hydrogens at this position here, and we were to consider its enol form, which would be this species. This is referred to as the keto with the carbonyl. This is the enol. All right. In this particular equilibrium, okay, it turns out that over 99% of acetone exists in its keto form, but only about 1.5 times 10 to the minus 4% exists in its enol form. Now, the reason for that is the keto form generally will dominate the enol form in an equilibrium. And that is because the carbon double bond oxygen has about 87 kilocalories per mole of energy stored up in it, as opposed to a carbon-carbon double bond, which has about 60 kilocalories per mole stored up in it. And so the carbonyl effectively is more stable than the alkene. And so in an equilibrium, equilibriums will always favor the side that is more stable. Okay. Now, that doesn't mean this is necessarily always the case. There are some other things you should consider, which is, well, what if you were to have some neighboring groups close by? So if we were to have, let's say, this species, which is called a beta keto, okay, ketone, so you have a carbonyl here that's at the beta position. In this particular system, if we were to draw out its enol form with one of those carbonyls, would look something like this. And in this particular case, the keto form versus the enol form, the keto form is about 24% of that equilibrium versus 76. So this is a significant change, okay, in which is being favored here. And so now the enol form is actually being favored. And so what is it that is, I guess, giving this enol an advantage over the ketone? Okay, so if you look at the system closely, you should be able to see, well, one thing that stands out is this system is conjugated. Okay, the double bonds are, effectively interacting here. Those pi electrons are, overlapping. And another feature as well is there's some kind of intramolecular hydrogen bonding that's occurring here as well. So this has a couple of things going for it that kind of puts the enol form in that being favored in that equilibrium. Now let's look at one more example, which is kind of an extreme. But if you had, let's say, this ketone, all right, that ketone is in equilibrium with this enol here. And if you were to ask yourself, okay, which side do you think is favored? In this case, the keto is only about 10%, and the enol is about 90%, so this is even more skewed. You can say definitely you have conjugation, but what else is present here? Why this particular enol is favored over that ketone? So why is the enol so favored? Okay, well, the answer is, well, you have an aromatic compound. So because that's aromatic, that is that extraordinary stabilizing ability that favors that molecules will fight to keep and want to have due to having full molecular orbitals of pi electrons, bonding molecular orbitals, that is. So a little bit of review of some properties that we have talked about already. Now I want to go back to a reaction that we talked about in chapter 17, and that I said we would come back and address the mechanism, and that is the haloform reaction, which is going to be the first one that we're going to be talking about in this unit. So this particular reaction specifically is for methyl ketones. And so you have a methyl group here on that ketone, specifically for methyl ketone. And what we said in the last chapter, chapter 17, is that if you were to take this compound and treat it with at least 3 equivalents, okay, at least 3 equivalents of a halogen in the presence of base, followed by an acid workup, that would result in the formation of carboxylic acid and a molecule of haloform. Okay. Now, the way this works, and I think now it should start to make a little bit more sense, is that the base here is going to be able to deprotonate these hydrogens as they are alpha hydrogens. And so when that happens, you end up removing one of those alpha hydrogens. This is going to occur stepwise, so it means we're going to take these off one at a time, not all at once. So you end up now with negative charge here. There's two hydrogens here remaining, and this is our enolate. Now, this is going to be able to react with halogen. And once you do this, okay, these hydrogens here that are remaining, well, these are now even more acidic than the hydrogens that we started with because, well, now you have an electronegative element here as well. So that is also kind of sucking electron density out of those bonds. And so as soon as it does it the first time, well, the hydroxide is going to be able to go in and do this a second time. And so now you're going to have your second equivalent of your halogen. That will be able to add in. And so now you will have two X groups here. And again, adding two halogens, that's going to even make this even more acidic, this remaining hydrogen. And so hydroxide will be able to remove this as well. Okay. Obviously having an excess of hydroxide present when you're doing this. And now you can add your third equivalent. And once you've done that, you now have your three X groups, three halogens added into here. And the last thing now, there's no more alpha hydrogens, but the hydroxide, guys, is not only basic, but it's also nucleophilic. So you can get an addition reaction here to occur with the carbonyl. And this thing right here, it may not look like it, but this is actually a pretty good leaving group considering you have all of these halogens that could potentially stabilize a negative charge, which is exactly what happens. And so the elimination is you eliminate this CX3 minus species. And you produce carboxylic acid. Now, the hydroxide or this species is going to deprotonate this. And all of these steps are somewhat reversible, but this very last step is pretty much irreversible at this point. So you now have your equivalent of haloform, and you have your carboxylate that you've produced. So this is why you have to add in a second step acid to this to end up protonating that carboxylate to give you the carboxylic acid. Okay, so now having gone through that whole process, it should make a lot more sense now as to how and why you needed a methyl ketone to do this in order to kick out that CX3 group to produce the carboxylic acid. Okay, so I'm going to go ahead and turn the video around here real fast. Okay, so again, I apologize with some of the lighting issues here. I hope this was a little bit easier to see. I've been previewing some of these videos and I noticed it looked a little bit dark, and I hope that was a little bit easier to watch. So, so what we're going to be doing going forward here is we're going to look at a few more reactions in the next video that deals with alpha hydrogens. And so just some stuff to come is we're going to be looking at some more examples that deal with halogenation at the alpha position that don't necessarily, that's not going to end up producing carboxylic acid, but actually a halogenated species at the alpha position. And then we're going to be digging into a little bit more detail about thermodynamic and kinetic products. Just like something that we had talked about back in chapter 13, that is going to come back up again here and be very relevant as to predicting which type of products you can produce when you have more than one alpha hydrogen that's on different non-equivalent carbons. And so that's going to be coming in the next videos that we're going to be talking about. Okay, anyway, guys, I hope everybody's doing okay, and I will speak to you again soon. Take care. Okay, bye-bye.